You've spent weeks optimizing your CUDA kernel, calculating flops, and perfecting your math. On paper, your GPU is a beast, capable of trillions of operations per second. But when you run the profiler, the results are devastating. Your kernels are stalling. The compute units are idle. This is the CUDA memory ghost, an invisible force that haunts almost every high-performance application. The reality of modern GPU architecture is a massive disparity between compute speed and memory throughput. While a modern H100 can perform thousands of additions in the time it takes to fetch a single float from global memory, your code is likely stuck in the waiting room. To fix this, we have to stop thinking about math and start thinking about the plumbing of data movement. Today, we unmask the ghost by looking at the three horsemen of memory stalls: latency, uncoalesced access, and bank conflicts.
To understand why your kernel waits, we have to look at the clock. When a thread requests data from global memory, DRAM, it doesn't get it instantly. It takes roughly 400 to 800 clock cycles for that data to arrive. Imagine a chef who needs an ingredient from a pantry that is a 10-minute walk away. If they stop working until they get that salt, the kitchen stops. In CUDA, the GPU tries to hide this by switching to other warps of threads that are ready to work. But if all your warps are waiting for memory, the ghost wins. This is known as being memory latency bound. We aren't limited by how fast we can calculate, but by the round-trip time of a single request. If your kernel has low occupancy, meaning not enough threads to hide this gap, your hardware spends most of its life doing absolutely nothing.
The most common way to summon the memory ghost is through uncoalesced access. When a warp of 32 threads requests data, the hardware is happiest if those threads ask for a contiguous block of memory. This is coalescing. The GPU can fulfill this in a single 128-byte transaction. But if your threads are jumping around, thread 0 asking for address 100, thread 1 asking for address 5000, the hardware has to issue 32 separate memory transactions. You've just reduced your effective bandwidth by 32 times. It's like a mail carrier having to drive across town for every single letter instead of delivering to one apartment complex. This is why data layout, like using structure of arrays instead of array of structures, is the single most important optimization you can make in CUDA.
Even when you move data into the ultra-fast shared memory, the ghost can still find you. Shared memory is divided into 32 banks. Each bank can serve one request per clock cycle. If two threads in a warp try to access different addresses that happen to fall into the same bank, we have a bank conflict. The hardware has to serialize these requests, effectively cutting your speed in half or worse. It's a traffic jam at the bank teller. To avoid this, you need to understand your stride. If your threads access memory with a stride of 2, 4, or 8, you are likely hitting the same bank repeatedly. A simple fix? Potting your arrays. By adding a single unused element to the end of each row, you shift the alignment and let all 32 threads hit 32 different banks simultaneously.
If you can't reduce the latency, you have to hide it. This is where occupancy comes in. Occupancy is the ratio of active warps to the maximum possible warps on a streaming multiprocessor. Think of it as having enough backup workers. When one group of threads hits a memory wall and has to wait 400 cycles, the GPU scheduler instantly swaps them out for a group that is ready to compute. But there's a catch. Every thread uses registers and shared memory. If your kernel uses too many registers, the GPU can't fit as many warps on the hardware. Your occupancy drops, and suddenly you have no backup workers to hide the latency. The ghost returns. Balancing register pressure against thread count is the delicate dance of CUDA optimization.
You don't have to guess where the ghost is hiding. NVIDIA Nsight Compute is your flashlight. When you profile a kernel, look for the Memory Workload Analysis section. It will tell you exactly how close you are to the maximum theoretical bandwidth. Pay attention to warp state statistics. If you see high values for stall long scoreboard, you are waiting on global memory. If you see stall MIO, you're likely overloading the memory instruction pipeline. Modern profiling isn't just about finding slow lines of code, it's about identifying which hardware limit you are hitting. Once you know the bottleneck, be it throughput, latency, or pipe pressure, the solution usually becomes obvious. Stop fighting the hardware and start flowing with its architecture.
Mastering CUDA isn't just about writing parallel code, it's about mastering the memory hierarchy. From the massive but slow global memory, through the L2 cache, into the fast shared memory, and finally the registers, every jump is an order of magnitude faster. To banish the memory ghost, remember the golden rules. Coalesce your global accesses, avoid shared memory bank conflicts, and keep your occupancy high enough to hide the inevitable latencies. The next time your kernel feels slow, don't just reach for more math, look at the data. Because in the world of the GPU, the fastest calculation is the one that never had to wait for its data. Thanks for watching and happy optimizing.